My name is Rohan Dalvi, and I will be talking about the physics of Formula One.
The physics of F1, while complicated, can still be applied to the everyday cars we drive. Ever since the first Formula One championship in 1950, drivers, mechanics, and designers have tirelessly worked to bend the laws of physics. In the early days, weight and weight placement were king. Teams began experimenting with materials such as aluminum and magnesium. The biggest breakthrough of this era, however, came with the 1958 Cooper T43 and its revolutionary engine placement. While most cars had their engine in the front, the Cooper sat behind the driver. This allowed for a lower moment of inertia, or resistance to rotation, making turning easier. Additionally, moving the engine back increased the weight over the rear wheels, which were connected to the motor. In the equation, force friction equals mu Fn. Fn equals mass times gravity. This means that increasing the mass over the rear wheels increases their friction, which means more grip and less wheel spin while accelerating. Eventually, all cars would adopt this layout. The next major advance occurred in 1967. Until now, aerodynamics had been a little concern and were only used to reduce drag or wind resistance. Ferrari's founder, Enzo Ferrari, famously stated that aerodynamics are for people who can't build engines. All of this changed when designer Colin Chapman debuted a wing on his Lotus 49. The Lotus wing worked using similar principles to an airplane wing. Plane wings work by increasing airspeed over the top of the wing. According to Bernoulli's principle, this leads to more pressure under the wing than over it. This pressure causes lift. The basic design of an F1 wing is an upside-down plane wing. Now, there is greater airspeed over the bottom of the wing, causing higher pressure over the top of the wing. This pressure difference, called downforce, forces the wing down, effectively adding to the friction force of the tires. While this does also increase drag and reduce the car's speed in a straight line, the trade-off was worth it. Although the first iteration was a failure due to its flimsy design and caused many accidents, the groundbreaking idea combined with an influx of deregulated sponsorship money to kick off a never-ending race for more downforce. The next revolution in F1 aerodynamics came in the form of ground effects. First used in Formula One on the Lotus 78, ground effects worked by using Bernoulli's principle, quick flow, and the Venturi effect to turn the entire car into a wing, increasing grip and force friction. The Venturi effect is the resultant loss in air pressure when air flows through constricted space, and quick flow is a stronger version of Bernoulli's principle that occurs when one surface is moving in a different parallel direction than the other. Next year's Lotus 79 would go on to use this technology to win a world championship. Ultimately, F1 cars could not handle the speed gain from ground effects, and they were banned after 1982, a season which saw multiple severe accidents and 3 deaths. One of the most ingenious designs came in the form of the 1978 Brabham BT46 fan car. It featured a gigantic fan in the back to suck air out from beneath the car like a vacuum cleaner, maximizing ground effects. The BT46 stormed to victory in its debut race. It was immediately banned after rival teams caused an uproar. The cars of today are faster than ever, and we can calculate just how fast using equations learned in this class. Take Cops Corner at Silverstone. Because we have the velocity of the car in the corner and the corner's approximate radius, we can find centripetal acceleration. The centripetal acceleration in this corner is 49.231 meters per second squared, or about 5 times that of gravity. That means that in this corner, drivers are subject to 5g, or 5 times the force of gravity. To put that in perspective, a driver's head and helmet equal 13.78 pounds. At 5g, this works out to about 70 pounds that the neck must withstand 52 times each race. In comparison, astronauts hit a max of 3g. While the physics of Formula One may seem complicated, they are easily understandable and applicable in real life.